Section 4.3. Now we're trying to work out figuring out area of a region with a definite integral, and then we're going to try to tie geometry to that. We're going to try to figure out how that geometry can make things a little bit easier and how they relate to this concept called a definite integral. Well, what is a definite integral? We've talked about integrals already, and we said if I wanted to represent, I've dealt with antiderivatives and stuff like that, and we started with our integral symbol. Well, here's what's going to happen. If this blue function is my f of x, if I wanted to set up a definite integral, we know that it's going to start with an integral symbol and it's going to end with this dx thing. We've done that with indefinite integrals already. Well, what's going to happen now is we're going to start to use this in a little more concentrated fashion. And that concentrated fashion says I am integrating some function. What is it? In this case, it's f of x, that blue function. And we're integrating it with a starting value and an ending value. So if I'm starting with my lower bound here, what's my lower bound? I'm starting at a. My lower bound always goes on the bottom of that definite integral, and my upper bound always goes on the top of that integral. So my integral from a to b of f of x dx, and what this does is this whole thing, when we go through and solve it, represents the area under f of x between x equals a and x equals b. Area under f of x, and I should make a little note here about this area under f of x. This has got to be above the x-axis. Or basically between f of x and the x-axis. When we're talking about area, we're going to be trying to deal with this down to the x-axis according to what I've got going there. So we'll continue to play with this a little bit more. Set up a definite integral. So set up this thing that we just showed for this region. Well, what do I have on this one? It's like I've got a function, and you can't really see my x-axis and my y-axis right there. This is f of x equals 4, so we know that this is a 4 for a y value. Well, what do I have? I have it looks like I've probably got a square here, and it's kind of hard to see. We're going to make this thing go from, I think it's supposed to be going from x equals 1 over to x equals 5. So if we do this, we're going to integrate this thing from 1 to 5 of f of x. What's f of x? F of x is 4. We're integrating that thing with respect to x's. That would be my definite integral that we'd use to find this area. Well, if I wanted to find this area, a simple way would be to just say area is 4 times 4. That area would be 16 square units. And that 16 square units, if we knew how to figure out that integral, that's what that integral would result in. Okay, number 2, now I've got this function x plus 1. And again, I've kind of lost my x-axis and my y-axis. So this is now y is equal to x plus 1 for my function. And it looks like we're going from 2 to 6 here for my bounds. So if I wanted to write a definite integral, I'd be looking at integrating with respect to x. What function am I integrating? I'm integrating x plus 1. I'm integrating that thing starting at a lower bound of 2 and going to an upper bound of 6. And if I wanted to figure out how that integral would work out, I would just go ahead and do area right here. Well, this is a trapezoid if I want to do it that way. Or maybe you like it better saying, hey, that's I see a rectangle that's 4 units wide by 1, 2, 3 units tall. 4 times 3 would be 12 square units down here. And then this thing, it looks like, let's see, 6 plus 1 would say this is up here at, so this integral goes from, looks like about, this is at y equals 3. And this would be y equals 7 up there. So this would be 1/2 of a rectangle that's 4 units wide by 4 units tall. So that would give us an area here of about 8. So now if we put those two things together, 8 plus 12 would tell me my area under that curve would be about 20 square units. So 2 ways to represent it. We can represent it with this definite integral over here, and then this would be that 20 would be our actual area. If I look at number 3 and number 4, number 3, what do I see? It looks like I see the top. It looks like I see the top half of a circle. So if I wanted to find the area of this thing, and again, this time my axis didn't come through again. Here's my x-axis right here, and this circle has a radius of, I think, 3. So if this thing has a radius of 3, that means it's coming up as far as 3, over to 3, over to negative 3. If I want that area, it would be 1/2 of pi times 3 squared. which would end up to be, I think, 4.5 pi. So my area would be 4.5 times pi square units. And if I wanted to represent that as an integral, I would be integrating with respect to x again. So where are my x's going from? My x's are going from x equals -3 would be the smaller, to x equals +3 would be the bigger. And what is my function? My function is that square root of 4 minus x squared. And if we knew how to do that integral, we'd end up with an area of 4.5 times pi. Last but not least, when we get to this number 4, so number 4, we don't have to worry about finding the area. We aren't going to be able to find this exact area anyway. We're looking for that shaded region. So if I go to set up my integral, it looks like I'm going from 1, 2, 3 here up to 6. So my integral with respect to the x's, well, what are the x's doing? The x's are going from a smallest 3 to a largest 6. And what's the function I'm integrating with respect to? I'm integrating that x minus 1 quantity squared. And that would be my definite integral that I would use to find each of those areas. So geometry relates with this new thing that we call a definite integral. We don't know how to solve that definite integral yet, but one way to solve it is always to come back to this geometry thing.